Hello. Today we shall be still proceeding on our lessons concerning integration, and in this lesson we shall be listing a few of the properties of the definite integral, and these properties help you in carrying out integrals much more easily. So concerning the properties of the definite integral, we shall be focusing on some simple properties, and then we shall be speaking about what's called parity of functions that are amenable more easily to integration. And then we shall be speaking about an important theorem called the mean value theorem of integration. Now, the mean value theorem of integrals, it resembles very much the mean value theorem that we spoke about in our lessons of the application of differentiation. But the other one concerns the differentiation. In other words, difference between the function at two different points relating to the derivative at a point in between. Here, it's the integral, which is equal to the distance of from a to b, if you are carrying out the integral on a closed interval a to b, times the value of the function at a particular or at a point in between. So it's more or less equivalent to the other one, just a little slight difference. Now about simple properties of the definite integral. Here the functions, this function of course is a continuous, is equal to constant, but we do not mean to expose the properties of functions that are continuous, not at all, only that they have a definite integral. In other words, we are speaking about Riemann integrable functions, but we speak about properties of these functions when they have a special properties of their own, and these properties, as a matter of fact, they may help us conducting, as I said, or evaluating integrals much more easy. For example, when you have, for example, a function which is constant, of course here you don't need to do a Riemann integral or to do a Riemann sum in order to take the limit and calculate the integral directly. You know, this is a rectangle, it's a constant, though the area under the graph is equal directly to what? To the base times the height. So since the height is equal to c and the base b minus a, so your integral from a to b directly is equal to c times b minus a. Straightforward. So here are a list of some theorems concerning sums or difference, or when you have, for example, two functions f and g, they are both integrable on the closed interval a, b. Then first of all, when you integrate from a to a, of course here your Riemann sum is 0. Because there are no partitions. It's the same point, and therefore you expect that your integral from a to a must be equal to 0. You have a 0 area. Again, when you calculate the Riemann sum from a to b is equal to minus the Riemann sum from b to a, because instead of going forward from a to b, you go backward from b to a. So you expect your delta x to be here negative, and you expect that the integral from a to b is equal to minus the integral from b to a. For example, you wish to calculate the integral. This is an example that we saw before in our lesson of definite integral. We calculated using the Riemann sum. You remember the upper and lower Riemann sum, and you took the limit, and we realized that the integral from 0 to 1 to the square root of x dx is equal to 2 over 3. But then suppose you wish to calculate the integral from the definite integral from 1 to 0. So what you do, you apply the last result. It's equal to minus the integral from 0 to 1. So it's equal directly to minus 2 over 3. So you use as properties to facilitate integrals instead of going again through the same procedure of evaluating your integral. Again, this is here a property again of a definite integral. If you have two functions, for example, and what about, for example, the integral of f of x minus g of x? Suppose this is the graph of f and this is the graph of g. You directly notice that the dashed area here is equal to what? The area under the first graph minus the area under the second graph. Or you may say that the height of your function here, when you take the Riemann sum, if you wish to do so, is equal to f of x minus g of x. So what you do is, when you have the difference or the sum of two functions, the integral becomes equal to the integral of the sum of both integrals. In other words, the sum of the integral of the first function plus or minus the integral of your second function. So here, for example, you have x plus x squared, and you wish to evaluate the integral from 0 to 1. So it becomes equal directly to the integral of the first function here. So the integral from 0 to 1 of x dx plus the integral of your second function. But the first function is a straight line. So we may not do the Riemann sum, of course. It's an area of a triangle. and is equal to a base 1 of a height 1, so it's half. Whereas the second one, we saw it before. This is in our first lesson, introduction lesson of calculus. We saw that this was the first ever result discovered in calculus, because it was a result in integration and not differentiation. Applying the result of Archimedes, Archimedes found that the area, using of course our notation of integration, the area under the parabola, the graph of a parabola from 0 to 1 is equal to 1/3. So all you have to do is that you sum up both results here to obtain the area, the overall area, or the overall integral. Again, when you have a function multiplied by a constant, you don't need to carry on the integral from the start. What you do is that you calculate the area of your original function, and then you multiply by this constant. For example, you have here, evaluate the integral from 0 to 2 of 5 times f of x dx, and you are given f of x. So what you do, if you want to calculate this integral, you may calculate first the integral of your function, which is the original function. It's equal to 1 from 0 to 1, and equal to -3 from 1 to 2, which you can add them up. Of course, here your function is positive here, and here it's negative, so you expect your integral to be negative. Why? Because you multiply 1 by 1 to obtain 1, and here you multiply 1 by -3 to obtain -3, so the sum is equal to -2. Suppose now you wish to calculate the integral of 5 times this function. What you do, you multiply c, which is 5, times the integral, your original integral. So here again, since the integral of your original function is equal to -2, because you sum up directly the areas, here it's positive, and the other one, I have to remind you that areas are not equal to integrals. The area, you must take the absolute value, whereas integral may be negative or positive. And since your function was beneath the x-axis, so in this part from 2 to 3, it was from 1 to 2, it was negative. And therefore, the sum would be negative. So the original integral is equal to -2. So if you want to calculate the integral of 5 times the function, you must just multiply the constant, which is 5 times -2, to obtain -10. Again here, if you have a function and it is defined over, for example, a region, the closed interval from A to B, can you subdivide your interval into 2 sections, or 3 or 4 or 5, etc.? Yes, you can do so. And what you can have here, this is a theorem, of course. The integral from A to B would then be equal to the sum of 2 integrals. One of them is from A to C, and the other one from C to B. So here is your result. Here, in other words, your integral can be subdivided into the sum of different sub-integrals, if you may call them so, where each one is defined over a region, a partition of the region from A to B. So therefore, it's from you add up the 2 integrals, one from A to C and the other one from C to B. For example, here you want to express this into one integral. Here, what you can do is that first of all you have to invert the integral, the limits of integration. So you can say that this is equal to, instead of minus, plus, but from -2 to -1. And we said this before. So you have here the integral from -2 to -1 plus the integral from -1 to 0. So you end up with what? From -2 to 0. You just apply the theorem. So the integral becomes here equal to -2 to 0. In other words, you have to carry on the integral from A to B, then from B to C, or from A to C plus from C to B, and you end up with the integral from -2 to 0. Now you can also discover symmetry of your graph. For example, here you have a function which is integrable from on the interval from -a to a, but there is a parity here. In other words, you have f of minus x is equal to minus f of x. So since f of minus x is equal to minus f of x, then your integral is equal to 0. And you can prove this directly. You have here, for example, a graph like this, and this is here, the integral is negative, and here is positive. You have an integral from minus a. You can subdivide it into from minus a to 0 of f of x dx, plus the integral from 0 to a of f of x dx. So this part here you can fiddle with how you can take x is equal to minus y, for example. So this integral becomes equal to what? When x is equal to minus a, y is equal to a, and from x equal to 0, y is equal to 0, and here you have f of minus y, you substitute x for minus y, but dx is equal to minus dy, and this is equal to what? This is equal to f of minus y is equal to minus f of y. So here again it is equal to from a to 0 to f of y dy. But this is equal to what? You can interchange the limit of integration. This is equal to minus the integral from 0 to a. So you have here the integral from 0 to a, the sum of your two integrals become the integral from 0 to a of f of x dx minus the integral from 0 to a of f of y dy, which is the same, no matter what sort of variables you are using. So when you add them up from 0 to a and from 0 to a again, this is f of x dx, and this is minus the integral again of the same integral of f of x dx, so they add up to 0. So when you have a function which is has a parity which is odd, the integral of over an interval here, then the integral becomes equal to 0. Again, when the function is even, when you have, for example, a function f of minus x here, on both the integral here, both of them are positive. So what you do, the integral from minus a to a, you can do the same. To prove it, you can do the same thing. You can, here, for example, you can decompose this integral into two integrals, one from minus a to 0 and one from 0 to a. And then you prove that the one from minus a to 0 is the same as the one from 0 to a by, for example, substituting x is equal to minus y, and carry on the operation to realize that they both are equal. And therefore, instead of carrying out the integral from minus a to a, you say that this is twice the integral from 0 to a. In other words, all these properties facilitate your evaluation of the integral. When you directly realize that your function is odd, then the integral over an interval, then the integral is 0. When it is even, you need only to calculate half the integral and you multiply by 2 and you get the whole integral. Here your function is positive, and you have a mirror here. Your y axis works as a mirror. So since this the value here is equal to value there, so there is no point of carrying the integral from minus a to a. You need only to calculate the half of the area and then you multiply by 2 because the function is even. So here, for example, this function is odd. How would you know that? All you have to do is that you substitute x from minus x. For example, here f of minus x is equal to what? E to the minus, here minus x modulus sine of minus x. But then the modulus of minus x is the same as the modulus of x. And you keep the same sign here. So you have, but sine of minus x, we saw this before, your function of sine minus x is equal to minus the sine of x. So what you get here, what? You get here the negative value of the function. So you directly notice that f of minus x is equal to minus f of x, which means that your function is odd. And since it is odd, your integral from minus pi to pi becomes equal to 0. So you don't need to carry on the integral. Of course, this function is continuous. You may apply the fundamental theorem, but you may not need to do so. Why? Because since it has an odd parity, and therefore the integral is equal to 0. Again, this function here, it's even. Why? Because you see directly here that all the values of the function on the left-hand side of the y-axis are those on the right-hand side. So all you need to do is to sum up the area here and you multiply by 2. Of course, you may wish to prove that it's even. All you have to do is that you invert the inequalities here. You instead of minus x, you put x, and here you invert the inequality, so you get, instead of this rule, you get this rule. So actually this function is even, but of course if you know how to draw simple graphs, you realize that it's even. So your integral from minus 3 to 3 is equal to twice the integral from 0 to 3, and from 0 to 3 here it's a triangle, the area is equal to half, whereas here it's 2 times 1 again, which is 1. So your integral is equal to half, I suppose minus half, and then you multiply the area by 2. This is the same sort of property like the one which is even, except that it is not symmetric about the y-axis. It's symmetric about an axis here of symmetry, a over 2. And you wish to calculate the integral from 0 to a. So what you do, it's equal to twice again, and it's clear from the graph as a matter of fact. It's equal to twice the area of one piece here, one lobe here. We call it a lobe here. You have here, you can calculate the area from 0 to a by 2, and then you multiply it by 2. And in order to prove this, it's easy again. You can take, for example, a minus x. You can take a minus x is equal to y. In other words, here you take the area, you take the first integral, and then from a to 2, all you have to do is that you can take x. You can take a minus x is equal to y. So this transformed into when x is equal to a over 2, this becomes a over 2, and from when x equal to a is equal to 0. And then you substitute a minus x here, but this is equal to what? This is equal to a minus x is equal to y, and dx becomes equal to minus dy. And this is the same actually like this one, except you have to, what you do, in the limit of integration, you replace them one with the other one. So here, this becomes here, and this becomes here. And then you invert this sign, and you direct notice that this integral is the same as this one here, so you multiply by 2 to get your overall integral. So symmetry helps you in evaluating integral much more easily, because you don't need to carry on the integral over the whole domain. You may only calculate the area over one simple piece, and then you multiply by 2. And this is a useful property. They discovered that if you have a function which is integrable on a from 0 to a, then the integral from 0 to a is equal to the integral from 0 to a, and instead of x, you substitute a minus x. A property that sometimes we use in order to facilitate evaluating integrals. For example, this one here, we don't know how to calculate it. So what we do, we apply the theorem, and you substitute x by pi by 2 minus x, which is the upper limit of integration. And then you directly realize that since this ends up, this is the value here, cosine pi by 2 minus x is equal to sine x, and this one is equal to sine x plus sine x. So since this integral you started with is equal to this one, so when you sum them up and you divide by 2, you obtain the original integral, of course. But when you sum both integrals together, you end up with what? You end up with an integral of this sort. And this is equal, cancelled out, is equal to 1, and you know the integral directly is equal to pi by 2. So since the original integral is half of this one, and this one is equal to pi by 2, so you obtain the original integral pi by 4. And this is a trick that sometimes we use to evaluate integrals that are difficult to calculate. And this is another example here. You don't know how to calculate this integral, so what you do, you substitute x for pi by 4 minus x, and you realize that this integral here is the same as this one. What you do, you fiddle with the trigonometric identities until you end up with this one. But here, the logarithm of 4 divided by cotangent x minus tan x is equal to what? The ln 4 minus ln cotangent. But the ln cotangent, you realize when you remember our lessons of integration by parts, when you ln 4 minus ln cotangent, you get it, you bring it to the left hand side. So you have one what? You have twice the integral is equal to the integral from 0 to 4 of ln 4. And ln 4 is a constant, so you can carry on the integral directly. It's equal to pi by 4 times twice ln 2, and this is the value of the integral. In other words, you use parity is one way of evaluating integrals by simplifying the integrals, and this is another theorem which sometimes we have to resort to in order to evaluate integrals. Now, these are some results about integrable functions. As we said, integrable functions in general. And if you have two integrable functions, f and j, then first of all, if f is positive, then the integral is positive, because your region will be above the x-axis. For example, prove that 1 over 1 plus t squared is positive. Here we need not know the value of the integral. We only want to know whether it's positive or not. Of course, this value of integral it's what? It's the arctan. You remember this is one of the elementary function, because the derivative of the tan minus 1 of x, the inverse function of the tan, is equal to 1 divided by 1 plus x squared. But we are not interested in evaluating the value of function. Only we need to know whether this is positive or not. Since this is positive from 0 to 1, then the integral must be positive on the same interval. Again, sometimes, for example, you have a function which is greater than another function. Would this integral of the first one is greater than the integral of the second one? Yes, indeed, it is. Why? Because the region, since this f is greater than j, and actually you may use the previous result to prove this one. Why? How? By subtracting f minus j. Since f greater than j, then f minus j is positive, and if you apply the previous result, then the integral of f minus j is positive. In other words, that the integral of f is greater than the integral of j. And you realize here directly, since f greater than j, that the area under the first graph is greater than the area under the second graph. Again, this is an important theorem. Here, f is located or bounded between an upper bound capital M, a small value small m. So m need not be the maximum value of the function, because what we said here, the function is integrable, f and j only, or f. Since f is integrable, you may have a point at which there is a discontinuity. But since you have finite number of discontinuities, suppose even it is at this point or that point, it's not important, because since these are least upper bound or greatest lower bound, and the function is integrable on the closed interval AB, so you may bound the integral between the upper value m times b minus a and greater than m times b minus a. How you do this? Directly here. Here, look at the green graph. This is the graph of your function. And of course, the graph of your function here, the area under this curve, of course, it is smaller than the upper value of the function here, the maximum value of the function, or the least upper bound of the function, capital M, times the distance b minus a. Of course, the area of the greater rectangle here is greater than the area under the green graph here. And the area under the green graph, again, it's greater than the small m, which is the smaller value of the function, times b minus a. In other words, you have two rectangles, a great one, capital M times b minus a, and the small m times b minus a, and the area under your graph is located between these two areas. So, of course, if this is so, then directly you can say that since capital F, since f of x, the area from a to b, is smaller than capital M times b minus a and greater than small m times b minus a, so sure your integral will be is equal to a value in between capital M and small m, let us call it r times b minus a. So what you do now, since this is so, you can divide the integral I, which you call it I, you can divide I divided by b minus a, and what you obtain here, you obtain r. Your r is the main value of your function over the interval ab. And it's a nice result here, that since the function is located between a greater value and a small value, therefore it must be equal to a value in between. And this value here is called what? The mean value of the function, because you divide the integral divided by the base. And you may do so even if you have, for example, a greater, for example, interval of this sort. And you have a small m like this. This is here, this small m, and here you have capital M here. And you've proved now that the area, your integral, is greater than small m times b minus a, because it's greater than this area here. Whereas it's smaller than this great area here. It's smaller than this rectangle, the area of this rectangle, and it's greater than this rectangle. So it must be equal to what? To a certain mean value r times b minus a. Times b minus a. And this is the mean value of your function. And the function, of course, may not be continuous, but it's a mean value of between a greater rectangle and a smaller rectangle. Again, if you have, for example, a function f and you want to integrate it from a to b, here the function, as you said, here the green one here, sometimes it's positive, and on other interval it is negative. Of course, if you calculate the integral, you will find that plus here, negative this value here, so it must be smaller, the integral must be smaller than this area here. So if you invert this green graph here from this point till this point, you get, for example, the blue one here. So sure, the integral from a to b is less than what? The integral over from a to b of the same function in which the negative part here is inverted. So the integral of your function is less than, of course, the modulus of your function from a to b. But then your modulus here, so in other words, here you have the integral, the modulus of the integral is equal to what? The modulus of the integral is what? Is this positive part minus this negative part. You assume that your positive part is greater than negative part, or it's vice versa, it doesn't matter. But what you have here, what? The modulus of the integral. In other words, what you have is this plus sign, and you subtract this negative sign here. This is your integral, and then you take the modulus. When you take the modulus, you will find it, of course, less than the sum of these two areas here, because the other one, when they are summed up, they subtract from one another. Whether it's negative or positive, you take the modulus. But it is in any case less than the area under these graphs, the green one and the blue one here. So, and this one here, the green one and the blue one, which is the integral of the modulus, It must be less than the area of the great rectangle here, of course. And the great rectangle is equal to what? Is equal to b minus a times k. And k represent what? The maximum value of your function or the modulus of your function on the interval ab. So sometimes this helps you evaluating not values of function, but it gives you upper bound for your integrals. Again, if f is an integrable over ab, the modulus of f is so, and f raised to the power n is so also, and the product of two integrable functions is integrable, and when f is positive, the square root of a integrable function is positive, and these are a list of theorems. You don't need to go all the time to check the integrability of your functions. If your original function is integrable, once you can apply these theorems. Now, this is an important theorem. It's called the mean value of a function. And this we've seen before when we talked about the mean value theorem, the differentiation, or the mean value theorem of differentiation, and it is the mean value theorem of integration. Now, this theorem tells you the following. If f is continuous on a closed interval ab, then there exists a point zeta in ab such that this holds. And this is a very important theorem. Why? Because first of all, to prove this, we have to go back to our theorem. We said before that the integral from a to b of f of x dx, if it is less than m from a b minus a, greater than m b minus a, so it must be equal to what? It must be equal to a certain r times b minus a. Now, this function is continuous. You remember here. And you remember from the lesson of continuity, we said that if you have a continuous function, first of all, on a closed interval, then it must attain a maximum value and a smaller value. So actually, this integral here adheres or comply with what we have written here, that your integral is less than capital M, because it exists since function is continuous on a closed interval from the extreme value theorem, and is greater than a small minimum value of M times b minus a. So this first line here is satisfied. But then you apply the intermediate value theorem. This in the same lesson. We said that if you have a function continuous on a closed interval, and if it attains, for example, f of a at a maximum is smaller, doesn't matter, or if you take any value between a and b, and if you take any value r, and this value r is between two values of the same function on a closed interval, so there must correspond a point zeta or c, we called it then c, at which f of c is equal to r. So here again, from this line here is equal to r times b minus a. But this value of r is what? Is the value of r situated between capital M and small m. So since the function attains capital M and small m on the interval, this value of r must correspond a value, we call it zeta, at which f of zeta is equal to r. And from there on now, you have the integral of f of x from a to b is equal to r, which is equal to f of zeta times b minus a. And this is the theorem we have here. It's said that the integral of a from a to b over f of x dx must be equal to what? The base here, the interval b minus a, times the value of the function at a particular point zeta. And actually, you can write this in a different way. We can say that the integral from a to b of f of x dx divided by b minus a is equal to f of zeta. So this actually theorem is important. Why? Because suppose, for example, that you have here the curve of velocity, and you are traveling, for example, from Rome to Naples, and you find that, for example, you find that the distance is 200 kilometers. So if you divide, and this represents time, a and b are here on the time axis. So if this represent the area or the distance, in other words, because this is the velocity, if this represents the distance, you divide by the time of your trajectory, which is, for example, 2 hours, and you reach what? You reach something like your mean velocity, which is equal 100 kilometers per hour. But then the theorem tells you something more than that. It tells you that there is a point in between your route, between Naples and Rome, in which you attain this velocity of 100 kilometers an hour. Of course, from the theorem, you can calculate the mean velocity. This is simple. Anybody can do it by dividing the distance divided by the time, and you obtain the mean velocity or the mean speed in your trajectory, in your trip. But there is more than this. It tells you since you have a function which is continuous, your speed is continuous, of course, even if you stop somewhere, because your function is always continuous of your velocity. So since it's continuous, then there must be a point at which zeta, a point zeta in your trip, this is a time, this is an instant of time, or you have more than this instant of time at which the speed is equal to 100 kilometers per hour. So here, as I said, assume that the car is traveling between two cities with a varying speed. The average speed is v of t, and it is equal to what? It is equal to the distance divided by t minus t naught. So here, you can write it in a different way. This is, again, f of t. You integrate f of x dx from t naught to t1, from a to b. You divide it by b minus a, and you get the average speed. Or you can say that the distance is equal to the average speed from t1 minus t naught. But the most important thing, because of the continuity of your speed function, or the continuity of f, then there exists a point zeta in the trajectory in which you attain this mean value of the function. Here for example, you have a function which is, this is the graph of a half of a circle, and you wish to calculate the mean value of your graph. Here it is. Because the equation of a half a circle is equal to y is equal to square root of 1 minus s squared, and you wish to calculate the mean value. What you do is that you can calculate the area, and you divide by the base. Here it is directly. The integral from minus 1 to 1, but this is equal to pi by 2, because this is the area of a circle, which you know it offhand. It's equal to the area of a circle, pi r squared, and you have the radius is 1, so directly you have pi. So the area of a half a circle is equal to pi by 2. You divide by b minus a, which is 2, and you get pi by 4. So it means that the mean height of your half circle is equal to pi by 4. This is, again, a nice theorem. It tells you if you have two functions, and f is continuous and the other one is enough to be integrable, and such that one is positive, g of x is positive, then there exists a point zeta such that this integral holds. Let us show this nice result. You have here f and j. So you have here f is said it's continuous, so it must attain a maximum value and a minimum value. And then g is positive, so you can multiply by d, and you get fg times mg and greater than mg. And then you take the integral. So what you obtain, what? You obtain that the integral, m, you take m outside, and you take small m outside also, and this is greater than capital M, the integral of g of x ds, and this is the product of your f of x times gx dx, and this will be m integral of f of x, g of x dx. But then m, since m is continuous and it's located between bounded by capital M and small m, so sure there must be a point r in between the two of them, such it coincides with the point zeta on the x-axis. So you can, since this is less than capital M and greater than small m, so it must be equal. Again, the same sort of proof, r, which is equal to f of zeta times the integral. And you have here actually your theorem here, that the integral of a product of two functions, for example, f is continuous, the other one is integrable as positive, so the integral of the product of two functions is equal to a value of zeta in the interval of AB that belongs to the open interval AB, and such that times the integral of g. Actually, these kind of theorems, as I said before, all of them are list of properties of function that you may use them to facilitate integration. For example, I'll tell you, for example, one direct application of this. For example, you have square root of x, for example, times e to the minus, for example, x, the x, or for example, you may have even something like this, and you have the integral from 0 to 1 dx, and you are not interested. Actually, this sort of functions you can carry on the integration, because this is an algebraic functions, and you can use a sort of manipulation to manipulate with. But suppose sometimes you are not interested in knowing the value of the integral. You just want to know the bound for that integral. Your integral is situated between what values of here, what are the upper bounds and lower bounds of such an integral. In other words, as I said, sometimes, because in this situation, for example, the integral is easy, but in many situations you have functions that are not easy integrable. So what you do is that you just want to know an upper bound, I mean the location or the sort of heuristic value of your integral without the need to evaluate the integral. So what you do, here you have the function f of x. You can take f of x is equal to e to the minus x. You can take g of x is equal to square root of x. And you can apply the theorem. You know that f of x, e to the minus x here is because you know that e to the minus x is something like this. So f of x would be situated between in your interval from 0 to 1, which is the interval of integration. So it's less than 1. It's less than 1 and it's greater than 1 by e, because this is an exponential function, e to the minus x. It attenuates like this. So the maximum value in the interval from 0 to 1 is attained at 0, and the minimum value is attained at 1. So since f of x you know capital M and small m, so now you can say that the integral from 0 to 1 of square root of e to the minus x is less than what? Is less than 1 times the integral of what? Of the square root of x from 0 to 1, and it is greater than 1 over e, the integral again of from 0 to 1 the square root of x dx. And of course this one is easy because we saw it before. It's equal to 2 over 3. Remember in our last lesson. So what you are, you end up with what? That the integral is located between what? Between 1 over a, which is times 2 over 3, which is 2.45, and it is less than 0.667. So here, now, without evaluating the integral, you come up with a sort of bound, upper and lower bound for the integral. If you wish to manipulate more, you can use the previous theorem. If you wish to lessen the bound, because it's better, of course, to decrease the difference between upper and lower values of the integral, you can, of course, what you do, you can realize, this is, again, the function, m times b minus a, and greater than small m b minus a. And what you do, you can obtain upper, you remember on our lesson of maximization and minimization of function, what you can do, since you have a function which varies over an interval a, b, can you calculate the maximum value of the function and the minimum value? Of course, your function is square root of x times e to the minus x. You can calculate the maximum and the minimum value of this function over the closed interval using differentiation. And you rely on tests like the derivative, for example, it changes sign from negative to positive, or you can rely on the second derivative to be positive or negative to calculate the upper value, the maximum value of the function. This is continuous, and the smallest value of the function on the closed interval from 0 to 1. And then you substitute here, and then you do a table. You can calculate a table where at these critical values, you calculate the critical values in the open interval from 0 to 1, and then you check at the endpoints, capital M and small m, and then you can even bound better your integral. In other words, there is no one single way of bounding integral, but there are a set of ways which you can use these properties to bound the value of your integral. In case you are not interested of calculating integrals, you just need to calculate upper and lower values of these integrals. So at the end of this lesson, we have what we have exposed here are in our last lesson, we talked about the definite integral, and we said that definite integral is a more rigorous representation of integrals because really antiderivatives are not supposed to be integrals. They are deal only with, you can apply them only using the fundamental theorem, and the fundamental theorem has the shortcomings or the drawback of that it deal only with continuant functions. And then we give a general definition of what's called the Riemann integral. And in this lesson, we listed properties of the definite integral. Here, as you have noticed, we are not talking about particular kind of functions like continuous function. No, all these functions that we have listed or that we have exposed or that we have explained in this lesson concern function in general, whether they are only functions that are Riemann integrable and not necessarily that are continuous. And so all these properties apply mainly to integrable functions as a whole, and these are properties that we have listed here in order to help you or facilitate the method or the way in which you conduct or evaluate your integrals. Because sometimes you cannot evaluate your integral, but you wish to calculate, for example, upper and lower bound of these integrals. You may, for example, sometimes instead of calculating the integral over a whole domain, you may divide it into pieces in which the functions show some kind of properties like parity, etc. So these all are list of properties or behaviors that helps you facilitate or that helps you evaluate integrals in general. So at the end of this lesson, again, I wish to thank you for your attention, and I hope to have clarified these properties of definite integrals as a whole. And I wish to remind you, like every time I do, that all these lessons, whether this one, the preceding one, and the one that remains, are all uploaded to the site of the Uninettuno Telematic University. And on this platform, you can at your leisure time, you can revise all these lessons. And until we meet again, I thank you very much, and I wish you a very good luck.